We are used to things getting better, faster, and smaller, but we were not prepared for the moment time itself was defeated. A calculation that would have taken the world's most powerful supercomputers 10,000 years was finished in under 5 minutes. This single moment redefined computation, shifting us from the era of guessing to the era of knowing, and marking the irreversible arrival of the quantum age. Before we dive into how this machine changed the fabric of reality, I invite you to join our community of thinkers. If you seek to understand the hidden forces shaping our future, please subscribe to the channel and hit the notification bell. Your presence here is the first step toward mastering a world that is changing faster than we can blink. For nearly a century, we have lived in the shadow of the classical giant. From the first vacuum tubes to the billions of transistors etched onto silicon today, classical computing is a triumph of human engineering. It is a world built on the simplicity of the switch, the absolute certainty of the 0 and the 1. This logic built our cities, mapped our genomes, and connected the entire planet in a web of light and data. We have spent decades perfecting the art of flipping these switches faster and faster, believing that if we just had enough of them, we could solve any problem in existence. But as we reached for the stars and peered into the depths of the atom, we hit a ceiling that no amount of silicon could break through. The fundamental weakness of the classical giant is its reliance on sequential logic. It processes information like a person reading a book, one word at a time, one page after another. While it can read very quickly, it is still bound by the linear flow of time. When it encounters a problem with exponential variables, the classical machine begins to choke. Imagine a maze where every path you take splits into 2 more, and those split into 2 more, and so on. A classical computer must explore every single path one by one until it finds the exit. If the maze is large enough, the time required to find the way out exceeds the lifespan of the universe itself. This is the exponential wall, a place where brute force fails and where our greatest machines become nothing more than expensive heaters. Some problems in this universe simply do not yield to the flip of a switch. We see this most clearly in the world of molecular chemistry and materials science. Nature does not calculate in zeros and ones. It operates in a dance of quantum probabilities. When we try to simulate a simple molecule on a classical computer, we are forced to use approximations and shortcuts. We are essentially trying to draw a 3-dimensional world using only a 2-dimensional pencil. These shortcuts are fine for simple things, but they fail when we need total fidelity. To truly understand how a new drug interacts with a protein, or how a new material will conduct electricity, we need to speak the language of the quantum world. Consider the process of nitrogen fixation, the way plants turn air into fertilizer. Nature does this effortlessly at room temperature, but our industrial processes require massive amounts of heat and pressure, consuming nearly 2% of the world's energy. We cannot replicate nature's efficiency because we cannot simulate the quantum interactions of the catalysts involved. The limits we face are not technological, they are philosophical. A classical machine, no matter how powerful, cannot fully describe a quantum world because it is not built from the same fabric. It is an observer trying to describe a dance it cannot join. This is why we needed something more than just a faster computer. We needed a machine that exists in the same state as the problems it seeks to solve. This brings us to the qubit, a word that is often misunderstood as just a faster bit. In reality, a qubit is a different form of existence entirely. While a classical bit is either a 0 or a 1, a qubit exists in a state of superposition, where it is both and neither at the same time. Think of a spinning coin. While it is spinning, it is not heads or tails, it is a blur of both possibilities. This allows a quantum computer to hold a vast amount of information in a very small space. But the real magic happens through entanglement, a phenomenon where qubits become linked in such a way that the state of one instantly influences the state of another, regardless of the distance between them. Because of superposition and entanglement, a quantum computer does not have to explore the paths of a maze one by one. It can explore all of them simultaneously. It doesn't just look for the answer, it feels for the structure of the entire solution space at once. This redefines what computation even means. It is no longer about a series of logical steps, but about the interference of waves of probability. As you add more qubits, the power of the machine doesn't grow linearly, it grows explosively. Adding just 1 qubit doubles the computational space. By the time you reach 70 qubits, you have more states than there are grains of sand on all the beaches of the Earth. However, this infinite power comes with a crushing paradox. To perform these calculations, qubits must remain in a state of perfect quantum coherence. They are incredibly fragile, easily disturbed by the slightest vibration, a stray photon or a tiny change in temperature. This is known as decoherence, the process where the quantum system collapses back into a classical state because the universe looked at it. It is as if you are trying to build a castle out of smoke while a gale force wind is blowing. For decades, progress in quantum computing stalled not because our theories were wrong, but because the universe itself seemed to refuse to let us work in peace. Every time we tried to scale up, the noise grew louder. The more qubits we added, the harder it became to keep them isolated. This fragility created a sense of despair in the field, leading many to believe that a truly useful quantum computer was a mathematical dream that could never survive the messy reality of our world. We were trapped in a cycle of building machines that were brilliant for a billionth of a second and then immediately turned into junk. To move forward, we had to find a way to silence the universe, to create a place where the laws of physics could be suspended just long enough to find an answer. This silence is found inside the frozen cathedral, the physical home of the Willow chip. If you were to stand next to it, you wouldn't see a glowing orb or a sci-fi interface. You would see a massive stainless steel cylinder, a dilution refrigerator that keeps the core of the machine at a temperature colder than the deepest voids of interstellar space. It is chilled to nearly absolute zero, a point where almost all atomic motion stops. In this extreme cold, the Willow chip sits in total isolation, protected from the heat, light, and electromagnetic noise of the outside world. It is an engineered absence of disturbance, a vacuum within a vacuum. Inside this cathedral, artificial atoms are suspended in silence. They are manipulated by microwave pulses with a precision that borders on the miraculous. In this state, the quantum behavior of the qubits is finally allowed to persist. The machine is not just hardware, it is a sanctuary for information. It is the first time in history we have created a stable environment where the strange rules of the subatomic world can be harnessed for a meaningful amount of time. Willow isn't just a chip, it is the threshold of a new reality where we have finally learned to hold the smoke steady enough to see the castle. The breakthrough that truly changed the game, however, was not just better cooling but a shift in how we handle errors. In classical computing, errors are rare and easily fixed. In quantum computing, errors are the default state. For a long time, we thought we would need millions of physical qubits just to have a few clean ones. But with Willow, Google introduced a new era of quantum error correction. Instead of trying to make one qubit perfect, they learned to encode information collectively, across many qubits. This is the architectural shift from experiment to engine. By using what are called surface codes, the system can detect and fix its own errors without collapsing the quantum state. It is like a group of people holding a large sheet. If one person slips, the others maintain the tension so the sheet doesn't fall. This means that as we scale the machine, the fragility no longer multiplies failure, it actually helps suppress it. This was the moment the project moved from a scientific curiosity to a functional technology. We realized that we didn't need to defeat the noise of the universe, we just needed to outsmart it. This resilience is what allowed Willow to perform the ultimate showdown against classical limits. That showdown took the form of a task called random circuit sampling. To a layperson, it sounds like a useless academic exercise, but in the world of computer science, it is the definitive proof of supremacy. The task involves predicting the output of a quantum circuit that has been intentionally designed to be as chaotic and complex as possible. For a classical supercomputer, this is a nightmare of epic proportions. It has to track every possible interaction and probability, a task that grows more difficult with every passing microsecond. It is the ultimate test of brute force versus quantum fluidity. When Willow went up against the world's most powerful classical supercomputers, the result was not a close race. It was an existential blowout. The classical machine, using every trick in the book, would have labored for thousands of years to complete the task. Willow did it in minutes. This comparison rendered classical computation irrelevant for this specific class of problems. It wasn't about speed, it was about feasibility measured in cosmic time. It proved that there are doors in this universe that only a quantum key can open. The impossible had not just been challenged, it had been broken. But skeptics remained. They argued that being good at a random task didn't mean the machine was actually useful. To answer this, the team introduced something called quantum echoes. This was the moment the field achieved its first real flight in this experiment. Willow was used to simulate a complex physical system, and it produced new, verifiable scientific insights that had never been seen before. It wasn't just demonstrating that it could work, it was discovering new things about the way information flows through matter. This was the transition from a benchmark to a tool of knowledge. Quantum echoes allowed researchers to observe how quantum information spreads and then echoes back, a process that is nearly impossible to track classically. This wasn't just a simulation, it was an observation of reality through a new lens. It provided a way to verify that the quantum computer was doing exactly what it claimed to be doing, silencing the critics who thought these machines were just generating fancy noise. For the first time, we had a machine that could teach us something about the universe that we couldn't figure out on our own. With this new lens, the study of fundamental physics has become an experimental reality. We can now look at things like chaos theory, the arrow of time, and even the behavior of black holes in a lab setting. Quantum echoes enables us to simulate the way information is scrambled in extreme environments. We can explore entropy and time reversal in ways that were previously relegated to the realm of science fiction. The machine is essentially a laboratory for the laws of physics themselves. We are no longer just observing nature from the outside, we are probing its deepest mechanics. Think about the implications for our understanding of the universe. We might finally understand why time only moves in one direction, or how information is preserved when it falls into a gravitational well. These aren't just abstract questions, they are the foundation of our existence. By using Willow to explore these boundaries, we are opening paths to a unified theory of physics. We are beginning to see the code that runs the cosmos. This is the power of the quantum age. It doesn't just give us better gadgets, it gives us a deeper truth. As we move from physics to the practical, the impact of Willow becomes even more staggering. We are entering an era of universal simulation. Imagine being able to design a new drug with the same precision that we design a bridge. Instead of years of trial and error in a lab, we can simulate the exact molecular interactions of a compound within the human body. This could lead to cures for diseases that have plagued us for centuries, tailored to an individual's specific genetic makeup. The era of one-size-fits-all medicine is coming to an end. This extends to the very air we breathe and the energy we use. Quantum computers will allow us to design new catalysts for carbon capture that are efficient, enough to actually reverse climate change. We can create new materials for batteries that hold 10 times the charge of current lithium-ion cells, or discover superconductors that work at room temperature, allowing for lossless power grids. Willow is an engine for invention. It is the tool that will allow us to engineer matter itself, creating substances with properties that do not exist in nature. The impossible is becoming a list of tasks for the next decade. We must also consider the synergy between artificial intelligence and quantum computing. These are not two separate trends, they are a mutually amplifying feedback loop. AI is currently being used to help design better quantum chips and to interpret the complex data they produce. In return, quantum hardware promises to provide the massive computational power required for the next generation of AI. Current AI models are limited by the energy and time it takes to train them on classical hardware. A quantum-powered AI would not have these limits. It would be able to process relationships and patterns that are currently invisible to us. This partnership foreshadows transformations across every sector of human life. Logistics networks could be optimized to a degree that eliminates waste entirely. Financial models could predict market shifts by accounting for millions of variables in real time. Climate modeling could become so accurate that we can predict the path of a single storm months in advance. We are looking at a shift in human cognition itself. When we have tools that can think in quantum terms, our own ability to understand and navigate the world will expand in ways we can barely imagine. It is important to remember that Willow did not appear out of thin air. It is the result of a decade-long ascent, built on disciplined, incremental progress. There were no miracles, only thousands of small victories and even more failures. Each version of the chip, from the early 9-qubit designs to the 54-qubit Sycamore and now to Willow, built the credibility and the data needed for the next step. This journey proves that the path to a revolution is paved with patience. It was the steady accumulation of knowledge that led to this useful quantum advantage. We can now see a clear path toward fault-tolerant machines. The roadmap is no longer a series of ifs, but a series of whens. We have moved past the era of quantum supremacy as a mere concept and into the era of quantum utility. The technology is moving out of the physics department and into the engineering department. This transition is perhaps the most significant milestone. It means that the foundation is solid, and the structure is now being built. We are standing on a threshold, but it is not a finish line. It is the beginning of a marathon that will define the rest of the 21st century. In this new era, quantum computing is no longer an abstract layer sitting on top of reality. It is becoming a tool woven into the very fabric of physics. We are transitioning from being observers of nature to being participants who can compute with it. This is a profound shift in the human story. For thousands of years, we have used tools to manipulate the world around us: sticks, fire, iron, and silicon. But now we are using the fundamental properties of existence itself as our tool. We are coding with the same variables that God or nature used to build the stars. This brings us to a human lesson that goes beyond the technology. The story of Willow is a metaphor for perseverance. It reminds us that failure is not the end, but merely information. The very things that make quantum computing impossible, the noise, the fragility, the chaos, were the things we had to embrace and understand to succeed. We turned weakness into leverage. In our own lives, we often face exponential walls or problems that seem too complex to solve. The lesson here is that sometimes the answer isn't to push harder with the same logic, but to change the way we look at the problem. Curiosity, patience, and reinterpretation are the true drivers of breakthroughs. If we only ever look for the obvious, we will only ever find the classical. To find the quantum, we have to be willing to exist in the superposition of not knowing, to be comfortable with the blur of possibilities until the right answer emerges. As you move through your day, ask yourself, where am I using brute force when I should be looking for a new perspective? Where am I letting noise stop me instead of learning to work with it? The breakthrough you are looking for might not require more power, but a different kind of presence. The quantum age has begun, and it starts not with all the answers, but with much better questions. As the line between the impossible and the practical continues to dissolve, the responsibility for how we use these tools falls on us. Imagination has become our primary constraint. We are now limited not by what we can do, but by what we can dream of doing. The future is no longer a distant horizon. It is a calculation currently running in a frozen room. I want to thank you for spending this time with me, exploring the boundaries of what is possible. If this journey into the quantum world has sparked something in you, please subscribe and share your thoughts in the comments. What is one impossible problem in your life or in the world that you would want a quantum computer to solve? Let us start a conversation that goes beyond the surface. Until next time.